and poetry are similar is the way poetry manages how poetry manages its movement from from the concrete, the imagistic, towards its generalization, towards its abstraction, towards its discursiveness. And in mathematics, it's the same movement. We go from something that's very concrete, like 1, 2, 3, towards a, a generalization of the idea of number as the container, the holder of those numbers, like x. And then x gets associated, let's say, with the number 3, x equals 3. And that would be the association. X is the generalization idea. X itself can be a real number. It can be a natural number. It can be a rational number. And then accordingly, we will have to find the correct concrete instantiation of a natural number to stick in if x is a natural number.
Yep.
It has been designated as a natural number. Now in poetry, so the example in front of us here is a poem by Robert Frost called Fire and Ice, frequently anthologized. And Robert Garrett, can you tell me if the title of the poem is an example of a place in a poem which is imagistic and concrete, or is this a place in a poem or the title which is a generalization, an abstraction, or some notion? So what do we have here?
It's an abstract, or it's concrete. It's not.
It's concrete. Very good. All right. So just like before in mathematics, if you have some concrete stuff in a line, sooner or later the poet will give you its generalized, abstract instantiation of that idea. So fire, what do you think is associated with in the poem?
When we look at the poem, we see in line 3, fire is associated with desire.
With desire. Very good. So I'm going to put that here, even though you can't see the board, but we'll get to the board in a second. So fire is associated with desire, okay? And then the other concrete word in the in the title is ice, and ice is associated with, in the poem?
In line 6, we see the word hate.
Very good. All right. And that's how the movement is in poetry. We go from fire, very concrete, towards what it represents, what it stands for, which is desire. And the poet makes sure that he gives us the association. He makes sure that we go from eyes to hate or hatred, not eyes to indifference. And the poet makes sure that we go from fire to desire, not to something else. And so he specifies, just like X is specified to contain only natural numbers, for instance, then we can't put -2, we can't equate -2 to X, because X is supposed to be just natural numbers, a variable that takes natural numbers only. And here, the poet wants to make sure that he controls what the images, what the image of fire stands for. He does not allow the reader to associate it with different notions and different themes. He controls the whole narrative really well. Okay, all right. And then stop share and
continue on. All right.
So now we're supposed to keep it like that, right?
Yep,
okay here. So what I've done here, Robert Garrett, is I have the title here. And well, what do you think? Do you have any comments, or when you see the title?
What I was kind of noticing in the title is it looks like a statement in logic.
Oh,
like
brilliant. Wow, I wasn't even going to go there. Very good. And so
with what we've found for the abstraction, or Robert Frost has given us as desire and hate, we could make those two versions of want.
Okay,
where
all
fire
right.
is.
So you're saying we're going to have here fire will be associated with want, which is a synonym of the word desire. And then in logic, I would take the word and replace it with it's a symbol in logic, which is this, the logical and. And then ice would be the opposite of want, right?
Or as hate's the opposite of desire, ice could be the negation of want.
Negation, okay, so that's a word right here. So we're going to negate. Negation is what we're doing here. And so we're going to have want here. And you negate it by putting a not in front of it. Okay. And then we get this. And so if we assume, what's the next step? If we assume want is true.
Yep.
So let's do it right here.
Start with a truth table.
Yeah, so we're doing the truth table. Yes, very good. So want is true. Then this is
Has to be false, not true.
false. So not true. Let's do that actually, just to not want. So this is what's happening here. And so we have not true, because the value of want is true, not true, which is actually false. And the truth table tells us that if you have true, if you this is a conjunction of the value true and false, then this whole thing is actually false. And in fact, that's where the poem goes, right?
Yep.
Fire and ice. Either you have too much desire or too much hatred. Both of these things lead to destruction.
Yep.
And so false then stands for destruction. Okay. Of the world in the poem. And so what you just did, Robert, was take the title and reformulate it in the logical, as a logical statement in mathematics, and then figured out this conjunction, true want and not wants conjunction, these two statements, its truth value. And it turned out to be false, which matches with the idea of how the desire and its negation will both lead to destruction, to something false in the world. Very good. Okay. So I think we should be good. I think we should just continue, right?
Yeah.
Yeah. Okay. All right. So that was the poetic business here. So let's go to a concrete example. Not concrete example. Let's now go to mathematics and look at an example of a object in mathematics that is completely, extremely instance of so our set, let's call the set K. And so here's our set. Right now it's empty. And we're calling, so we've given the name, the set K, and then we have curly braces right here. The first element in the set is going to be Godzilla. So here we go. This is our Godzilla.
It's pretty impressive.
Oh, thank you. Yes. It's made in Japan. Godzilla. It also looks like a penguin. All right. Then we have a orange. Here's our orange. So I'm throwing in objects in no order. I mean, I could have put orange first, then Godzilla. And then let's have a house here. Make the house in blue. There we go, has a door, there's a window. Okay, so we have a set with 3 objects from the real world. All these 3 objects are actual objects that are found in the world. And now the idea is to take the set K and increasing generalization. Let's put this here. So our arrow here, the arrow is the arrow of generalization, increasing generalization or slash abstraction. Abstraction. Okay. So in fact, let's do this, right? Let's give it a title that's also very concrete. Things, it's a whole phrase, from this world. All right, I think that looks good. Now you get to choose the name of the set now. We're going to move down, and as we go down, this set will be reformulated, making it more and more abstract. And then we'll see if the abstract version, how tenuous or how weak the connection is. And that's why mathematics is so difficult. By the time we get to the highest level of generalization, we forget what it's anchored to. It's anchoring in the concrete. So we always have to remind ourselves.
Yeah.
And sometimes some people are really happy with abstractions and they can work with generalizations. But somewhere in their heads, they have to connect those things.
It doesn't do anything if you can't connect it back
Yes.
to the concrete.
So what letters should, so I'm going to go, we're going to make the, right now, the title, the name of the set is Things from This World. And let's give it a letter. So W?
Yeah.
Yeah, W works, right? Okay, very good. And now what's happened? We have, this is concrete. Things from This World is a very concrete name. And W is now an example of abstraction.
Yep.
And yes. Okay, and it is, yes. I'm just making sure. All right, so what's the first step here? Actually, in fact, let's do this. I've shortened, sorry, you'll have to fix that. But fixing your iPad is easy.
Yep.
Let's have a one-word title for our set.
World. Okay.
Okay. And then I could even call it a fancy worldiness.
Yeah.
Yeah, but we'll just stick with world. That's good. Godzilla becomes
a word.
a word. God. Godzilla. Okay, can't make. There we have Godzilla or Godzilla, as they say.
Yep.
And then orange becomes literally the word orange. And the house becomes the word house. So this is definitely a okay. This is definitely the first line here, definitely super concrete. Now we move towards a higher level of generalization. We went from the concrete to the next level of generalization. Let's keep going, right? And at this stage, the connection between this connection is still strong. The connection between the concrete and its generalization is still strong. So let's break that completely. Now we're going to use the letter W for the word as we decided earlier.
Yep.
And then Godzilla becomes
Lizard.
Or the letter G,
Mm. Mhm.
orange becomes
Oh,
very good. And house becomes
H.
H. Now, is there any connection? How how are these two related? It's a very weak connection between the concrete and its generalization. Weak connection between the concrete and its generalization. So if I look at this, can I reconstruct and get back here?
No.
Because G could now stand for
Goat.
good, goat,
Good. Goat.
goat. O could be owl now.
Yep.
It could be anything. H could be husband,
Yep.
right?
Huge.
Yeah. But all we have to do in mathematics is remember that there is this G stands for a certain, but anyways, this is where what happens is this is what we run into in mathematics, and it frightens people and you go into a panic mode. This everybody can handle, including kindergarten kids.
Yep.
Right? Okay. All right. That's why when you're in kindergarten and you don't know how to fit a shape in a peg, if you can do that, you can see the abstract version, right?
Oh,
So
that is totally, yeah.
Yeah,
'cause
right.
The abstract version is the
Right.
square or triangle.
So here we have, let's say there's a circle and a triangle. This is the generalization of the shape triangle. And then here's the circle. And then you give a kid an actual sphere, and you're supposed to stick it in here. If you are good with going from the concrete instantiation of something, and you can associate it with the generalized version, there's the abstract version of just this, then you can put that in.
Well, you've removed dimensions.
Yeah.
You've simplified
You
in the
simplify.
abstract.
Yeah.
And it's, yeah.
Very good. And that's why this toy is in those kindergarten schools. Yeah. So today, now we know why. Okay, all
If I
right,
taught
let's,
kindergarten, I'd call everything a set. I
Yeah.
just use super sophisticated mathematical knowledge.
I remember that was the only thing I learned in kindergarten was I could count from 1 to 100 and do that, and that was it. Then it took a while before I got somewhere else. Okay, let's go to a set, and we're going to do some other things. We're going to see how there are two ways to uh, what. So all those three examples of sets, they were all set roster. Uh, they were in the roster form, or what is it? It's called uh, roster form or listing. We just listed the objects. So here's our set. Let's give it a name, A. So A is a set. What's a set? Set is a bag that can contain objects. And we're going to throw into this bag 3, 4, and 5.
Yep.
Okay. And this is the roster form of declaring a set or listing method. Listing method. And what we want to do is we're going to rewrite this set using the what is called set builder notation. Okay, so A is a set that contains X. So
Okay.
how do we read this? We're going to read X as This is X. So I'm going to give notes right here. X is read as all numbers X. Okay, I could even put all natural numbers X, because this thing is a subset of the natural numbers. It's also a set of real numbers, but anything like that. So I'm going to say, so when you see X here, remind yourself what you're looking at is, don't just think of this as this is a number, this is a symbol that can hold many, many numbers. And at this point, we haven't specified what kind of number. It could be a natural number, it could be integer, it could be rational, it could be real, it could be complex. So one of the first things we're going to do is specify that. So our next step is actually, let me rewrite this. We need more space. So X belongs to set of natural numbers. Or in fact, the best way to read this is X is a natural number. So the three ways to read this. And the correct way for this to read it is, so I'm going to give you the three different ways. This is X is a natural number. So this is this symbol here. And sometimes we can also say X belongs to the natural numbers, or X, what's the third term? Belongs to and in.
Yep.
X is in the set of natural numbers. But this is the one that's the useful. So X, so we've just given the type of this. So, and now the question would be, what is the set of natural numbers? Let's write that out in the roster form. 1, 2, 3. There's a set of natural numbers right there. So A is what? A subset, as in it's a subset, but not the same. So I don't have a line here of this thing here. Okay, so at this point, what can A contain?
Only natural numbers.
Infinite number, and only natural numbers, and any and all, and I don't know how many. And what we want is, we're trying to rewrite this in the set builder notation, right? We just did the first step. We limited that, which type of numbers, natural numbers, and then we need to limit this. So I'm going to put, we need to impose a condition on X.
Yep.
Okay, so we're going to put X here. And the condition that we're going to impose, we're going to use this relation of less than to do that. So this is a relation and it's called, so this is a relation less than. So here we go. I'm going to put this relation of less than right here. So what do I need on the right hand side now?
Need a greater than.
So
Okay.
X is less than. So what number should I put here?
6.
6. If I put 7, would it work?
No.
Okay, 6. So any number less than 6 can be in the set. So right now, if I let the condition, if this was my property that I'm imposing on my set A, so if this is my property that I'm imposing. That is property on X. So this is the actual term, P of
Yep.
X. If I leave it like that, what are the members of the set A?
1, 2, 3, 4, and 5.
Very good. That does not match with that. So we need to bring this down here. Very good. And then what should I stick there?
The 2.
2. 1 will again not work because it will then
2,
include
3, 4,
2 in the
5.
set. And here we go. This set and these two sets are equivalent or same or identical. Okay, so the second, this one, the one, the set builder notation is the frightening one that scares people. You look at this one and everybody's cool. 3, 4, 5. You see that, you need to read stuff. For instance, I forgot to talk about this bar here. This stands for such that. That notation right there. Okay, you know all this, unfortunately. Is that true?
Yep.
Yeah, let's keep going.
Some of it.
Now let's do, let's do a very generalized way of defining a set here. So, and I'm not going to name it. I'm going to say X in, and then I'm going to have a such that right here with the bar. What should I put here? I want to go to a high level of generalization. I want to give a grid, a formulation that can apply to any set in the world.
I would put R.
You would put R, I would put S. That's what the book does. So any letter other than the special set. The list of special set is, these are our special sets, right? Natural numbers,
NZI
integers,
or
rational numbers, and real numbers, and maybe even complex numbers. This is our list of special sets. And over here, because this was still closer to the concrete, we put N here. So rather than put one of these, we put S here. So then S can be one of these. So this is again a high level of generalization. And then on this side, we need to put the condition that we have to impose on X. So X is in S such that a certain condition is imposed on it. And the most generalized way of saying that we have a condition on the right-hand side of the vertical bar is to write P of X.
So this is our most generalized set. That
Almost there, yes. This is the super generalized set, and very good enough for most mathematics. But what if we don't want this set just to be these objects, right? Right now, this set is actually can have potentially actual natural numbers or integers or rational numbers or complex numbers. This could be full of complex numbers. But what if we wanted to have a set that can have anything?
yeah, if we want to put Godzilla in there, how do we do
Exactly.
that?
How do we do that? So we could do this, because S here stands for things that look like that, the special sets. So right now, we could just have X here. So now X can be anything. And then we, of course, impose a condition on it to delimit what goes in. This is at the highest level. And then this is, how do we say next highest? Okay, so highest level, very high level of generalization. So this basically is a definition of how to do set builder notation. Okay. And so what does this allow us? Well, what this allows us is, for instance, if I have a set, and this is when I'm going to use the word R, a set like the Russell set that we'll be looking at later. R is a set that contains all things X. Right now, over here, this X was, how do you read this X? All numbers X in S, right?
Yep.
Robert, yes?
Sorry,
Yeah.
combined my apps on my iPad and whatever.
Are you using Notepad, Note one?
Yeah.
OneNote?
Notability.
Oh, okay. There's another app, but anyway, we can discuss that later. So this is all numbers X in S, and S is one of those special sets. Here, this is all objects X. It can be anything. So I put X here. This is all objects X. X could be Godzillas. X could be whispers.
Yep.
All the set of all whispers. Or we could make this interesting. And the PX that we put here is X is a set. And so what this condition does is it gives us a set like this. It will have, let's say, a set with,
Oh, so we've created a set of all sets.
yep,
Whoa, meta set.
yes, sir. Every set in the world will be in here. So when you see X here, you're saying, you say all objects X, and when we say X is a set, we're saying all, this is, the set R contains all sets, because the word all is already here. So when we put the P of X on it, the property, this property says that now set R is a set that contains all possible sets in the world, including itself, which is where the paradox comes in. Okay,
Yeah.
that's